All right, guys, are there any questions over the homework assignments before we start the lesson today? Any questions over the homework assignments before we start the lesson today? Question over the homework. Thank you. Now, the first thing we're going to be looking at is addition and subtraction, simplifying these with addition and subtraction. Now, we're able to add or subtract like radicals if the roots are the same and the number inside the radicals are the same as well. So when we look at this here, we've got the fourth root of 10 plus 7 times the fourth root of 10. Now, since both of these are fourth roots and the number inside of them is 10, it means we can add these two together. Now, the first one, how many fourth roots of 10 do we have? We have one of them. The other we have 7. So if we add these two together, we would have 8 fourth roots of 8 fourth roots of 10, because if we have 1 fourth root of 10 and we add 7 to it, we have a total of 8. Now we can also do this when we have fractional exponents, because when we look at this here, we have 8 to the 1/5 in both of these here. The first one we have 2 of them, and the second one we have 10 of them. So we have 12 times 8. That's it. Now, again, for us to be able to add or subtract, the roots have to be the same. For C, they are both cubed roots, but the number inside of them has to be the same as well. The first one's 54, and the second one is 2. So that means if we're able to add or subtract one of them, we have to decrease it or rewrite it. So if we look at 54, taking the cubed root of 54, we need to see if we can, guys, we need to see if we can be able to write the cubed root of 54. Now 54, if we look at the factor tree, one number that we know that is a factor of 54 is 2. And what times 2 gives us 54? And if we factor 27, it would be 3 and 9, and 9 is, so 54 is the same as 3 to the third times 2. So that is helpful for us because it means that we can rewrite this as, instead of the cubed root of 54, we have the cubed root of 3 to the third times minus. Can we take the cubed root of 3 to the third? Yeah. According to the properties, we could split this up as 3 to the cubed root of 3 to the third times the cubed root of 2. Now the cubed root of 3 to the third is 3. Now that we've rewritten the cubed root of 54 in simpler terms, now can we subtract them? So the 3 times the cubed root of 2 minus the cubed root of 2 would be, guys, would be what? So we have 3 here. How many do we have here? 1. So 3 minus 1 would be 2 cubed roots of 2. So for this here, if they're not already, the number inside them is not already the same, we need to simplify one or both to make them be the same.
What do you, what do you use this in real life?
Yeah. do it for cubes volume. Talking about fractional volumes with the lengths of cubes, cubics. Any questions on this here? Let's look at these next ones here. So the next one we have is the 7 times the fifth root of 12 minus the fifth root of 12. Because if we have 7 of them and take one away, we have 6. Since we do have 9 to the 2/3 in both, we do 4 plus 8, which is times 9 to the 2/3. So we need to find the cubed root of 40. So one of the easier ways to find it is with our factor tree. What is one factor? 2 and 20. We could have done 4 and 10. Any of these would work. But 2 and 20, 20 would be 2 and 10. 10 is? So we have 3 2's. 2 to the 3rd times. So we'll still have the cubed root of 5. But the cubed root of 40 we can rewrite as the cubed root of. Now we could split it back up and do exactly what we did on the last one. But the cubed root of 2 to the 3rd. What is the cubed root of 2 to the 3rd? If the index and the number match, the cubed root of 2 to the 3rd simplifies out. And it's still being multiplied by the cubed root of. So the cubed root of 5 plus 2 times the cubed root of 5 is? Guys. Guys. So with these here, when we don't have them with the same number and root, we simplify 1 to get it to be the same. Any questions on any of this here? Any questions on anything we've done so far? Any questions on anything we've done so far? Now, we can still do this simplifying with variables. But the issue comes in really when we take the even root with an even exponent. Because, as we have here, the 4th root of 3 to the 4th. 4th root of 3 to the 4th. So we take the 4th root of 3 to the 4th, and we write this out. The first thing we can do is figure out what 3 to the 4th is. We can do that in a calculator. 3 to the 4th is 81. And the 4th root of 81 is 3. Because we know that the 4th root and 4th power, guys, thank you, simplify out. Now, if we do this with negative 3, the 4th root of negative 3 to the 4th. Well, negative 3 to the 4th power is what? Negative 3 to the 4th power is positive 81. Because it seems like it would, but because the 3 is negative, the properties don't hold true with that there. So when the number inside is positive, we do end up with a positive. And when the number inside is negative, we end up with a. So to take both of these into account, when we think of the fourth root of x to the fourth, well, indeed, the numbers would simplify out. The fourth root and 4 would cancel out. But when the x started out as negative, it became, and when it was positive, it still stayed. So to bring that into account, we have to put the absolute values of x. As long as the power is odd. Our final power here is 1. It's odd, so we need to put that there. Now, if it had come out as x squared, we don't need it because the square takes care of any sign change. Now, we will look at those and see those here. I will not take all points for the homework if you don't include them, but we will cover them here so that you can see those. So let's look at this first one here. The cubed root of 64, y to the 6th. Now we're going to use our multiplication property first. Because I have two things multiplied together, we can rewrite them as each one of them times each other. So we can say the cubed root of 64 times the cubed root of y to the 6th. Now, one thing that we can do with any of these numbers, so the cubed root of 64, what we can do in the calculator is take the cubed root of 64. And if it gives us a nice number in the calculator, we have it simplified and we're done. And if it gives us a decimal, then we need to actually use the factor tree and simplify. So the cubed root of 64 is 4. And since it gave us a nice number, we can go on and simplify it. If it didn't, then we would need to actually go through our simplification or simplifying processes we've done so far. Guys. Now the other one we have is the cubed root of y to the 6th. So we need to simplify it if we can. And we're going to be able to simplify it, especially if the exponent inside is bigger than the index, bigger than our root. So 6 is going to be bigger than the cube, 3. And we need to simplify that down. Now, it might not be easy to see what the cubed root of y to the 6th would be. So what we can do is rewrite it as a fractional exponent. And our property with this here is the nth root of a to the x is equal to a to the x over n. Root of a to the x is equal to a to the x over n. So for the fractional exponent of the cubed root of y to the 6th, the numerator of this fraction would be the exponent of, and the one on bottom would be 3. So the 4 is already simplified. What would 6/3 reduce to? Two over 1 or 2. 6/3 is 2. Since we don't have any more fractional exponents, the cubed root of 64y to the 6th is 4y squared. Now, because the variable has this square, we don't need the absolute value bars with it. And also, since we're taking the cubed root, we don't need the absolute value bars either. Any questions on how we did A? Any questions on any of this here? Let's look at the next one, the fourth root of x to the 4th over y to the 8th. Now, the first thing we can do is use our division property, our quotient property, and split this back up into the 4th root of x to the 4th over the 4th root of y to the 8th. Now, part of the reason we can split this up in this way is because they're both going to simplify out. Now, at this point here, the numerator, the 4th root of x to the 4th, we can see how that simplifies, but we're going to go on and write both of them as fractional exponents. So the fourth root of x to the fourth. The number on top is going to be 4. The number on bottom is going to be 4. The denominator, our y, the fourth root of y to the 8th. The number on top of the fractional exponent is going to be, guys, and the denominator is 4. Now at this point here, we can simplify each of these exponents. The numerator 4/4 is going to reduce to 1, so we'll just have x. The denominator 8/4 reduces to 2 over 1, or just 2. Yes, sir. Yes. Any questions on this so far?
No, sir. You're doing an excellent job.
Now, since the numerator, we took the even root of an even power, we need to put absolute values. Because whenever we take the even root of an even power, and the result gives us a variable with an odd exponent, so 1, 3, 5, 7, we have to add the absolute values to it to adjust for a sign change. Now, if it had been left as x squared instead of just x to the first, we wouldn't have needed it, because a square, if it's negative, it becomes positive. Or if it's positive, it's going to stay positive. But this here would be the final answer. Any questions on any of this here? And again, if you notice with most of this here, like yesterday and the day before, we're just manipulating what we have to get it written in a simpler form. Let's look at the next one here, the cubed root of 27d to the 12th. Guys. Now for this here, we can rewrite it as our two terms being multiplied together. We can write it as the cubed root of 27, thank you, and the cubed root of d to the 12th. Now if we look at this here, the cubed root of 27, if we can plug this in and get a nice number, that'd be very helpful. So we can look at the cubed root of 27, and it is 3. Since it does simplify nicely, we can just replace it. If it hadn't, we would go through the process like we've done already of rewriting it in simpler terms. Now the cubed root of d to the 12th. Now we can rewrite this as a fractional exponent and then simplify it from there. Now the numerator of this is going to be the exponent attached to the variable, which is 12, over the root, which is 3. Over 3 reduces to 4, or 4 over 1. So it simplifies to 3d to the 4th. Questions on any of this here? Any questions on anything we've done so far? Okay. Let's look at the last one of this type. Since we have a quotient, the first thing that we can do is split it up into the two parts. So we can split it up into the fourth root of x to the 4th over the fourth root of y to the 16th. Now between these two, the numerator, we can see that we can actually take the fourth root of it. Because the fourth root of x to the 4th would be what? X. Because if the index, the root, and the exponent are the same, they cancel each other out. If we wrote it as fractional exponents, it'd be x to the 4/4. And And the 4/4 would simplify to 1, so we just have x. Now the denominator, the 4th root of y to the 16 would simplify to 16 over 4. The 16 on top, it comes from the exponent, and the 4 is our root. Now 16 divided by 4 simplifies to 4. So we have this here. Now I will take this as the final answer on the homework, but mathematically we would need to put the absolute values with the x to be completely correct. So I will take it with the absolute value or without. I will take either one. Any questions on any of this here? Any questions on anything we've done so far? Let's look at this one here next. So when we look at this here, we want to write each expression in simplest form, assume all variables are positive. Now the all variables being positive just means we don't have to put absolute values in like we did on the last few, but we still need to simplify this here. Now, not everything will simplify, because if we look at the first part, the 5th root of 4, can we take the 5th root of 4? No. So that means not everything is going to simplify out of the radical. There will be some that do, so there's going to be some variables or numbers that can come out of the radical, and some that are going to stay inside. Now the first thing we can do is split these into the different parts. Split them into the different parts. So we'll have the 5th root of 4, the 5th root of 8, the 5th root of 14, and the 5th root of c to the 5th. So the 5th root of a to the 8th, 5th root of b to the 14, and the 5th root of c to the 5th. Now we can rewrite these as fractional exponents. Now we'll leave it as the 5th root of 4, mainly because the 5th root of 4 doesn't simplify, doesn't reduce. It's going to stay in the radical. Now for our a, b, and c, we can rewrite these as fractional exponents. So a, fractional exponent, the numerator is going to be what? 8, the denominator is 5. B, our numerator would be 14, the denominator is 5. And lastly, C's fractional exponent would be 5 over 5. Any questions on this so far? Now the reason we're doing this is to, one, see what comes out of the radical and what stays in. Because if we think of these as fractional, or improper, not improper, as mixed numbers, we can see what the whole parts come out and the fractional parts are what stay inside. So 8/5, how would we rewrite this as a mixed number? So 1 and 3/5. And what we can do is see, so 8 is the numerator, and we can see how many groups of 5 we can remove from it. So if we subtract 5 from 8, we get, all right, so we get 3. Yeah. Can we subtract 5 again? No. So we have one whole group that comes out, and we have 3 that are left over. So we have 1 3/5. With B, we have 14/5. So we need to see how many times or how many groups of 5 can be removed from 14. So we can say 14 minus 5 is 9 minus 5 is, we can't subtract 5 again. So we have 2 whole groups that come out and 4 that are left over. So as a mixed number, 14/5 is the same as 2 and 4/5. C, to rewrite 5/5 as a mixed number, it would be 1. Because 5/5 reduces to 1, so it isn't nice. Fractional exponent. Any questions on how we got to this point here? Now, to rewrite it back in simplest form, we'll still have the 5th root because some of the numbers, some of the terms are going to stay inside the radical, some are going to come outside. Now, since we couldn't take the 5th root of 4, the 4 stays inside the radical. That takes care of this part. Now, A, the whole terms of our mixed number come outside. Since the whole number is 1, a to the first comes out of the radical. Now, how many would stay inside? Whole number is what comes out. Inside would be part of the 3/5. And according to the property, the nth root of a to the x is the same as a to the x over n. So we're talking about 3/5. 3 is our exponent. So we would have a to the 3rd inside. And the bottom of the fraction, that 5, is the root. That's our 5th root. So the 3/5 tells us that 3 a's stay in. Let's look at b. How many b's would come out of the radical? 2, because our whole number is 2. And how many will stay inside the radical? Our fractional exponent is 4/5. So we would have b to the 4th because our 5ths, the denominator is our index, our root, and that's our 5th root. And the last one, we have c to the 1st. So 1c would come out, and because it is a whole number, we don't have the fractional exponent anymore. There are none left inside, telling us this reduces to ab squared c times the 5th root of 4a cubed b to the 4th. Any questions on this here? Now, again, I need to reorder these here, but I want to go on and look at this one here. I want to look at another one of this type before we move on to the next type of problem. Any questions on what we did on the last one? So when we look at this here, we need to simplify it. We need to simplify the roots because whenever there is a number or exponent bigger than the root, we need to reduce it down. So the first thing we can do is break this up into its parts. The cubed root of 2 times the cubed root of a to the 13th times the cubed root of b to the 3rd times the cubed root of c to the 8th. We need to rewrite it in these parts here. Because if we look at this here, a to the 13th, b to the 3rd, c to the 8th, their exponents inside the radical are bigger than the root. They're bigger than 3. So each one of these is going to reduce. Now we can't take the cubed root of 2 because if that had actually been 8, then we could actually take it because the cubed root of 8 is 2. Guys. Now, when we look at the cubed root of a to the 13th, we could rewrite this as a fractional exponent because the cubed root of a to the 13th would be a to the 13 thirds. B would be to the 3/3, and C is going to be to the 8/3. And from here, we can rewrite these as mixed numbers. You can rewrite each one of these as a mixed number. So if we look at 13/3, so we can see how many times we can remove 3 from 13 to give our whole number. It's going to be 4. 13 minus 3 is 10. 10 minus 3 is 7. We can do it again. 7 minus 3 is 4. 4 minus 3 is 1. So the number of whole groups of 3 we can take out of 13/3 is 4. And what we have left over is 1/3. With B, well, 3 minus 3 is 0. So we'd have one whole group, and we wouldn't have any fractional thirds remaining. And lastly, C. So with 8, we could take one group of 3 out, 2 groups of 3 out, and we can't take any more after that. So we'd have 2 and 2/3. Any questions on this here? So our cube root, we would still have the 2 because the 2 did not simplify, did not reduce. With A is to the 4/3, which tells us that we can take 4 A's out of the radical. And how many are left inside? Our 1/3 would tell us that we have 1 left inside. B is to the 1st. So we do bring 1b out of the radical. Since it doesn't have a fraction part of that exponent, that's all we have. We don't have any left inside the radical. C is to the 2/3, so that means 2 C's will come out of the radical, guys. And how many are left in? Would be 2. And that is it. We know it's in simplest form when the powers of the variables and numbers inside the radical are less than the root, less the number in the V. Any questions on this here? Any questions on anything we've done so far? Let's look at this one here. So we're going back to this one. X over the cubed root of y to the 8th. Now, again, we cannot have any variables or any radicals in the bottom of the fraction. We can't have a variable and a radical in the bottom of the fraction. Really just no radicals in the bottom of the fraction. So we need to be able to simplify the cubed root of y to the 8th so that we don't have a radical there. Now, let's look at this as a fractional exponent, because it might be easier to see it as a fractional exponent than it would be as the cubed root of y to the 8th. So it would be 8/3. So the variable, the exponent with y8 goes on top. The index of 3 goes on bottom. Well, 8/3 reduce nicely. Well, no. 8 divided by 3 is not a nice number. What is the next number after 8 that will divide by 3 nicely? So, how many more y's do we need to get there? Because we're going to multiply top and bottom by y over y. And whenever we multiply like bases, we add the exponents. So we need both of these to be thirds, our cubed roots. We would need 1/3. Because we have 8 y's, if we have one more, 9/3 would reduce nicely. Guys, so on top, we multiply them together. Because x and y are different bases, we are just going to say we have x times y to the 1/3. Now the denominator, since we multiply like bases, we add the exponents. 8/3 plus 1/3 is 9/3. And in the denominator, the bottom of this fraction, 9/3, 9 divided by 3 is 3. Since we don't have a fractional exponent in the bottom of this fraction, it means the radicals in the bottom are now simplified. They simplified out. But the numerator, we can rewrite this y to the 1/3 as a fraction or as a radical. Since the denominator of the fraction is 3, its root would be 3, and the exponent with y would be 1, or we can just write it as y. So x over the cubed root of y to the 8th in simpler form, or in simplest form, is x times the cubed root of y over y cubed. Questions on any of this here? Now we'll finish this up